Hello, my name is Lu Gan, and I'll be presenting our work on energy-based linear robots tuning traversability modeling by deep inverse reinforcement learning. This work was done in collaboration with Dr. Jessy Grizzle, Dr. Eustice, and Dr. Maani Ghaffari from University of Michigan. To motivate our work, I'll play a short video from our previous work on self-supervised tuning traversability modeling for bipedal robot Jessy. We first used LiDAR point clouds and robot trajectories to build an elevation map. And based on geometric features such as the step height, roughness, and slope, and also the corresponding robot capabilities, we built a 2D traversability map from this elevation map. And we project the traversability score onto color image plane for traversability labeling and train a neural network to predict traversability from unseen images. Other works define tuning traversability cost as ground reaction score, maximum forward velocity, etc. These works are all manually defined quantity as traversability cost and learn it in a self-supervised or supervised fashion. However, the manually defined quantity may not fully capture the traversability the robot is experiencing. Therefore, we turn to inverse reinforcement learning to learn it from demonstration. Inverse reinforcement learning has been applied on tuning traversability modeling for autonomous vehicles. This works model tuning traversability cost as a native reward function and use maximum entropy deep inverse reinforcement learning algorithm to solve it. The reward function is estimated using a deep neural network, giving some environmental features phi of each state S. And the network can be trained by state visitation matching and backpropagation using demonstrations. More recently, researchers incorporate some handcrafted kinematics features, such as average velocity, into a framework. There are two problems when we apply inverse reinforcement learning-based method for linear robot tuning traversability estimation. It can suffer from the model fidelity due to the incapability of modeling more agile linear robot motion using handcrafted kinematic features. Also, it can suffer from the suboptimality of demonstrations due to the insufficient feedback received by demonstrator. In this work, we propose to incorporate robot proprioceptive feature learning in an IRL framework for linear robots tuning traversability modeling. And we extend the MEDIRL framework into a trajectory ranked MEDIRL framework and use locomotion energy as trajectory purpose label to alleviate the suboptimality issue. In our problem, we model the process of linear robot walking on local terrain as an agent following a Markov decision process. The trajectory is defined as a sequence of state action pairs followed by the agent. And the demonstration is a set of trajectories collected from expert operation. We try to recover the underlying reward function, which explains the demonstration. In order to encourage the disentanglement between the reward of traversing a state, which is concerned in this work, and the reward of terminating at a state, we define our state states to include path states and goal states, and we model path reward and goal reward separately. The traversability cost is defined as a negative path reward. To learn effective inertial features directly from raw sensor measurements, we design an inertial branch consisting of 1D convolutional layers and concatenate the learned inertial features with environmental features to estimate a path reward map and goal reward map. Here, the theta p and theta g share most of the network parameters. Second, to deal with the suboptimality issue of the demonstrated trajectories, we introduce a pairwise trajectory ranking loss as the trajectory purpose label and use average energy consumption to rank trajectories. The average energy consumption is defined using robot joint torque and joint displacement measurements from the entire trajectory and averaged along that trajectory. By adding the constraints of lower AEC corresponds to a higher trajectory rank and corresponds to a higher return, the framework can learn the reward function across trajectories and is able to plan a more energy efficient trajectory. The overall framework is shown in this figure. In each iteration, two batches of trajectories are sampled to compute the pairwise trajectory ranking loss. And the network is trained by minimizing this loss at the same time backpropagating the MEDIRL gradient from state visitation matching. To evaluate our method, we collected data by expert operating a Mini-Cheetah robot equipped with a depth sensor, IMU, and a NVIDIA computer on different types of terrains on campus. We generate demonstrations from both exteroceptive and proprioceptive measurements. The environmental features are elevation map and elevation variance from elevation mapping and the color map. The inertial features are learned from raw IMU signal from the inertial branch. We first quantitatively evaluate the effectiveness of initial feature learning using the original MEDIRL framework. Our method with inertial feature learning achieves the best future trajectory prediction results compared to our method without the inertial feature learning and the baseline method using handcrafted kinematic features, which shows the learned inertial features can improve the model fidelity without increasing the state dimension. Those are some quantitative results of 3 methods. From the left to right are estimated past reward, goal reward, and predict future trajectories. The ground truth future trajectory are overlaid with a color map in the left column. To evaluate the effectiveness of energy-based reward extrapolating, we simulated a Mini-Cheetah robot to follow the optimal trajectories generated from both methods on the input elevation map, and compute the average energy consumption for all test samples. The difference in the simulated AEC corresponds to about 7 minutes of extra operation for Mini-Cheetah robot, showing our method can learn an energy-aware traversability cost and predicts more energy-efficient trajectories. Here are some examples of the robot following optimal trajectories from both methods on given elevation maps. The optimal trajectory output from the trajectory ranked MEDIRL tend to walk around the bumpy areas and choose more smooth terrain. The main limitation of this work is the simplified discrete states and actions are unable to fully capture the agile motion capability of later robots. However, adding more dimensions comes with an exponential increase in the computation complexity. Designing a hierarchical action and state space and solve it in a trackable IRL framework is an interesting future research direction. Thank you.